Hello, and welcome to our Kubernetes Washington, D.C. meetup. This is a bi-weekly virtual meetup at this point. Today we have Oleg with us, and Oleg is the CTO at Kubler. He's going to go over hybrid Kubernetes environments with Submariner. Submariner is a CNCF sandbox project, and it's an open source project. So Kubler can reach out to Kubler or Oleg at Oleg CH. If you have any questions, please feel free to add those in the chat. And at the end, we may also have time to take live questions. In terms of housekeeping, we have a channel on slack.kubernetes.io. When you join, you look for Meetup DC channel, and you can chat with us there to recommend any topics, or if you have anything that you want to share with the team, you are very welcome to do that. Additionally, we also have a community page up at community.cncf.io/Washington-DC. This is where you can also sign up for future events, and you can view recordings and presentations of the past events. So that's a great resource there. And then we also obviously upload all of the recordings to our YouTube channel. We are going to share that URL as well. It's right here. So if you look for DC Kubernetes meetup, you should be able to hit it, but we can also share the URL. With that, I'm going to stop sharing, and I'll ask Oleg to take it over and just give us the introduction of Submariner and how to make it work.
Perfect. Thank you. Thank you for him for introductions. I just first of all, can everybody hear me?
Yep. Sound loud and clear. Thanks.
Perfect. Yeah. And so I won't stay on this introductory slide for long. CTO at Kubler, and at Kubler we develop enterprise Kubernetes management system called Kubler, which allows you to essentially deploy Kubernetes clusters at scale in any cloud, on-prem, in virtualized and private cloud environments. But today topic is not about Kubler per se. It's about Submariner, and more generically about intercluster connectivity. So different ways you can connect Kubernetes clusters across environments, across locations, and about Submariner as one of the most generic ways of doing that. So I will use Kubler in this demo to set up Kubernetes clusters, but generally speaking, this same demo, after you have Kubernetes clusters brought up using any means, should work with any clusters. I mean, with Kubernetes clusters that are deployed using any other tools as well. So before going to Submariner per se and connecting different clusters, first of all, let's go through a quick and brief overview of Kubernetes networking in general, and starting from that, we'll be able to discuss what it means to connect Kubernetes clusters. And by the way, so if you have any questions, just shoot them in the chat, or if you want to unmute yourself and ask them, maybe easier to tackle them right away when they're hot. Okay, so going back to Kubernetes networking, let's look at how Kubernetes networking is structured on a high level. So first of all, normally a Kubernetes cluster runs on a set of physical or virtual nodes, machines, servers, and each of those servers is clearly connected to some kind of network, and each of those servers has its own IP address or a set of IP addresses. And when we strip everything else. So this is what we will refer to as a physical network in this presentation. So nodes can talk to each other, and this is done on the physical network level. So on top of that, and usually infrastructure, whatever it is responsible for this connectivity, on this level. So it may be your data center physical network, or it may be your AWS VPC with subnets and routing configured for those subnets. But this is a underlying and fundamental way to connect physical nodes and whatever you run on top of that. On top of physical nodes, you run Kubernetes components, and Kubernetes, together with some components called CNI plugins, is responsible for setting up what we call here overlay network. So overlay network is a virtual network on top of physical network. It has completely different and normally, not normally, but almost always non-intersecting set of addresses, CIDRs. Those addresses are configured on within Kubernetes components when you configure Kubernetes. So, and this set of addresses is in turn split into two, pod CIDR and service CIDR. So every pod, every container you run on Kubernetes gets its own IP address within that overlay network. And then there are also services, also network constructs introduced by Kubernetes and used to provide stable endpoints for pods and containers. So those services also get each their own IP address from services address range. Now the last layer on top of that, service discovery layer, Kubernetes service discovery layer works based on a set of conventions that Kubernetes introduces and a component called, generally speaking, in-cluster DNS. And in most cases, it's implemented using core DNS, open source DNS server, which was designed and is mostly used with Kubernetes as in-cluster DNS server. So what that core DNS does, core DNS talks to Kubernetes API and translates DNS names like this. You see here there are several components to that DNS name that allow you to address services by their name. Not only services, it actually also creates those names for each pod in your cluster. It also creates such names for so-called stateful sets, but we won't go into a lot of details here. So most important part is that core DNS essentially looks at Kubernetes API, selects services running in your Kubernetes cluster, and allows you to translate names like that, that consist of the service namespace name, and then a stable part like SVC cluster local into the service IP dynamically. So when you have a service, you can always connect to it by name. Now we are more or less ready to talk about what it means to connect to Kubernetes clusters. So first of all, this connectivity, network connectivity, when you have one cluster running, let's say on the east, another cluster running on the west, or vice versa here, actually. The simplest thing you can do, you can connect their physical networks. But note those differently colored components of their addresses only if their address spaces do not intersect. And there are different ways of doing that. You can set it up using VPN tools. You can set it up using cloud-specific tools like VPC peering, for example, in AWS or Azure network peering. In the data center, you can do that setting up routing correctly, or maybe those physical networks are already connected and you have a flat network space in your data centers so that the clusters can talk to each other directly using physical addresses. But there is also a level of overlay network that you may want to connect to make sure that pods can talk to each other across clusters. So pods in one cluster can talk to pods in another cluster. And again, there are several ways of doing that. And in most cases, it is very specific to what kind of CNI provider or CNI plugin you are using in that overlay network. So you can use specific CNI capabilities for that. Like, for example, Calico is a CNI provider based on BGP and routing. Clearly, it can be configured to route those imaginary addresses packets to other subnets, and indeed you can use Calico specific capabilities to connect two overlay networks set up in different clusters. So, and as long as physical networks are also connected, packets between pods running in different clusters will be able to cross this gap. But this is not all. Of course, IP addresses and IP connectivity is good, but you also need to be able to use some sort of meaningful names for those services, for service discovery, especially when you have pods coming and going and services deployed and undeployed. So to make sure that this works as well, you need to somehow connect DNS layers, service discovery layers. And again, this is done usually by connecting core DNS servers running in different clusters. So in this cluster, you can, in this cluster, you can let core DNS know that if, for example, this domain name is requested, it should forward request to this DNS server and vice versa. So this DNS server will forward requests for that domain name to the other core DNS server. And because they refer to each other by IP, so this will work as long as you have this layer connected. So as you can see, it's very beautiful. Each layer very beautifully relies on underlying layer capabilities. So this is connecting Kubernetes clusters in most generic sense. But note that here, strong requirement is that IP addresses and domain name spaces are not intersecting. We have to carefully plan our clusters before we deploy them to make sure that all those addresses will be different across all your clusters. And this may be a problem when you are talking cluster peering at scale, when you have dozens of clusters, and or when you have very dynamic situation where you deploy clusters and remove them often. So that may be a problem. And there are ways to work around that. So even if you have clusters that have intersecting physical networks or overlay networks and or domain spaces, domain namespaces, you can connect them using a sort of shared address space in a hub spoke manner. So when you use something on each of these levels to route corresponding packets, to a set of addresses that is not intersecting with either of these clusters address spaces and is shared among a set of clusters. And again, this can be done. So you cannot then connect networks directly, but you can set up routing on all these levels, routing and forwarding on all these levels in such a way that selected services from one clusters are exposed in this shared address space, and selected services from that cluster are exposed here as well. And all of those exposed services are accessible from all connected clusters. So we'll talk about both scenarios here. So, and we'll show how Submariner can be used to do exactly that. Now, talking about Submariner, what is Submariner? So Submariner is essentially an operator for your software VPN. So Submariner is an open source project. You can use it in any context without limitations. And what it does, it runs a set of components that can, through a so-called broker namespace, exchange information about their VPN endpoints. They also can exchange information about exposed and imported services and about network within connected clusters. Another part of their functionality is maintaining gateway nodes, so which allows to achieve high availability and load balancing automatically. So one of the problems with VPN connections, with VPN peering of networks, is availability. So, for example, you can easily set up a VPN connection, site-to-site VPN connection using OpenSwan or LibreSwan or any other VPN software of your choice, OpenVPN, for example. The problem is that most of them are either very difficult to configure in a highly available manner, so that they can automatically fail over, or you need some kind of hardware support to make sure that this failover works. So with Submariner, it's not a problem really. So with Submariner, you can dedicate a set of nodes, a group of nodes in your cluster, and mark them as gateway nodes. And as long as those nodes have public IPs to which a peer can connect, and Submariner will automatically mark one of those nodes active and maintain others as passive. And when active node goes down, it will designate another passive gateway as an active one, and announce this change through broker to other peered clusters. So, and all of that is done by Submariner components running in all those connected clusters. So, and also, of course, Submariner components running on every node of each of the connected clusters are responsible for reconfiguring IP tables or NF tables in such a way that, or actually not, I'm sorry, I think it does touch IP tables, but most work is done on routing level. So routing rules so that every node knows where to route packets that are addressed or that are sent to another cluster. And the same is true for exported and imported services. Now, service discovery works in a similar way. So when you have Submariner components running in those connected clusters, it also starts a component called Lighthouse, which in turn consists of Lighthouse agent and Lighthouse operator, I think. And those components plug into in-cluster DNS service so that shared services can be also shared services address space can be also available within all of the connected clusters, and the addresses of shared services are available to components that request them. So I already talked through Submariner components, and essentially this is a formal list of responsibilities that Submariner takes on. Now let me switch to the demo. So what I did, I used our Kubler demo environment to deploy two Kubernetes clusters, one in Azure, one in AWS. And when you, or if you look at our project, our demo project on our GitHub account, GitHub Kubler Submariner demo, you will find clusters directory here, which contains those clusters specifications that can be used with Kubler to deploy those clusters. And those specs already include some configurations in those clusters that are necessary for Submariner to work. And I have summary of those settings here, showing the structure of this cluster specification. So first of all, cluster spec contains this network section that allows you to customize how cluster network works. And you remember that we talked that some of the address spaces in those clusters need to be non-intersecting for some of the connection scenarios to work, which is why we specify it here. Let me find this section here. Yeah, we specify it here in the cluster spec, saying that here for this cluster, for example, for AWS cluster, we will use this address space for pods and services. We will use cluster1.local in cluster DNS domain. And by the way, here in the same network section, we also connect our DNS server in this cluster to DNS server in the other cluster. It will not work until VPN connection on the overlay network level is established, which Submariner does, but at least we declare it in our cluster so that it's ready to start working at any moment. So other elements of this specification include, configuration of those clusters, physical structure, like for AWS, for example, we are running on spot instances in specific availability zones to make it a little bit less expensive. We configure additional ingress security group rules to make sure that ports that Submariner requires to be opened are opened. And again, this is a part specific to AWS cluster. In Azure cluster specification, similar things are done using Azure specific security rules, etc., etc. So the last part that I wanted to pay attention to is additional packages deployed in that cluster. So Submariner is deployed as a set of Helm packages, and why set is because one of those packages doesn't require any specific configuration, but another package, when you deploy actual Submariner operator, needs to be configured to be able to talk to broker. So we will deploy the generic part as a part of this cluster specification. So here we have a packages section which deploys two Helm charts with configuration specific to Submariner. And then we will follow through the demo steps, and you will see how actual connection, cluster connection happens. So this is what relates to cluster specifications. So I talked already about a little bit different specification for Azure and AWS clusters. So, and now we can just switch to our demo, and README there contains step-by-step instructions. Only the first two sections are specific to Kubler. So here it just tells you to deploy two clusters through Kubler. So if you use other means, feel free to do that with k8s, Kubadem, Kind, or any other cluster deployment tool of your choice. And I already have those clusters up and running with all components green, including those two additional packages with a few instances there. And I have them configured here in my console. Let me know again if you if it's too small. I can make it a little bit bigger. You can see that for each cluster we have a kubeconfig file downloaded. So now I can just check that you can see both of these clusters nodes. Now let's go and connect those clusters using Submariner. So first of all, some quick set of common variables, and this is why we couldn't include code or deployment scripts for Submariner that would actually connect clusters into the cluster specs, because before those clusters are up and running, we don't yet have those connectivity parameters to let them know. So if we had a third cluster that we use as a broker storage, we could actually deploy Submariner operators into that as part of our cluster specification deployment. But here I decided to simplify it a little bit and just use one of those two clusters as a broker space. So let's generate some parameters, common shared key for Submariners to Submariner operators running in two clusters to be able to set up secure connection and the broker connection parameters. So those are just a set of environment variables populated using command line tools. And the next step, let's actually join, first we'll join a AWS cluster. And it's done by deploying a Submariner operator Helm chart with those parameters that we have just generated. So while it's deploying and it's done, so we now deployed this Helm chart in AWS cluster, and very similar command with a little bit different parameters to deploy Submariner operator into the Azure cluster. And while it's deploying in the Azure cluster, we can check how it looks like in AWS cluster using Kubernetes dashboard. So in that cluster, now we have, let me see, for some reason I don't see namespaces that I would expect to see there. Here it is. So we see two namespaces. One of them is Submariner Broker, and it doesn't run any pods actually. So when I talked about Submariner architecture, and when we talked about Broker here, you see it's called Broker namespace. So Broker for connected Submariner clusters doesn't have to be active. So Broker is just a namespace in any Kubernetes clusters, and it is used by connected Submariner operators to exchange information. So each of the operators here publishes some information in this Broker namespace, and each Submariner operator reads shared information from that Broker namespace. So it doesn't have to be active, it doesn't have to be scalable or big, it doesn't have to be available most of the time even, because Broker is only needed when significant configuration changes happen. So nothing will die if Broker is not available for some time. At the same time, it is necessary to share changes in configuration. So when gateway is switched from active to passive, Broker better be active and available for this information to be distributed to all connected clusters. Now, the other space is Submariner operator. And here we do have a number of pods running. So you will see here there are route agent pods, those that are responsible for route rules on every node. There are gateway pods running on gateway nodes, the operator itself, lighthouse, etc., etc. So this is indeed the active Submariner components. So now, as we deployed both Submariners, we can check. There is a command line tool that Submariner provides. So using that command line tool, we can check the connection status. And indeed, we can see that connection was established. It tells us which gateway. So currently, as we configured our Azure cluster kubeconfig file, so this command line tool checks with our Azure connected cluster, and it shows information for that cluster here. So this guy is used as a gateway, as a remote gateway. It shows you endpoints, active and passive, that are local, and it shows the remote, etc., etc. A lot of information here that can be useful. Now let's check if we have connectivity between clusters. So first of all, I will run a model applications, a model application, so which consists of two daemon sets, so that we can test connections between pods running on every node and a service. So those pods, well, on one hand, they can serve as a connection targets. So they open a port and wait for a connection on port 5000. On the other hand, we can use them as targets for our command line calls, which we will use to test connections from one pod to another. Okay, so we created service and two daemon set in one cluster and service and two daemon set in another cluster. And we can check how they are starting here in our dashboard, or we could just use command line and see that the containers are creating for all of those pods. And now they're up. So to test that that connection works from one pod to another across clusters. So the first our test is actually looping through clusters as a source. So first we will test connections from AWS cluster, then from Azure. In each cluster, it will select all of the pods. And again, from each of the pods, it will try to connect to each other pods in another cluster. And let's just run this script. And we will see, and by connect, I mean we will use kubectl exec command going into each of those pods and running curl to IP address of the peer pod. And as you can see, from every pod in AWS cluster, we can connect to every pod in AWS and Azure cluster, and vice versa. From every pod from Azure cluster, we can connect to every pod in AWS and Azure cluster. Similarly, we can test pod to service IP connections. So it's a bit shorter because while there are 3 pods in each cluster, they all are served by a single service. But still, we can see that every pod in every cluster can connect to each service in either AWS or Azure cluster. What else can we test? Similarly, we can test connections to service addresses rather than IP. So testing their names, DNS names. As you can see here, we are trying to connect to test service server. Test SRV pod service in default namespace in cluster 1, and then in cluster 2. And again, each pod can connect to them, which means that each pod can get valid responses from the DNS server, whether it tries to address its own cluster's service or the other cluster service. This all was nice and good, and it all stayed within this picture. So we essentially, using Submariner, we set up connection on physical and overlay network layer level using routing. So each cluster knows how to route packets to the IP addresses. And we used direct cluster-to-cluster in-cluster DNS forwarding to connect their DNS namespaces. To test this picture, so we can pretend like those two clusters are that we cannot connect those two clusters directly, and we can try Submariner's way of exporting services. So, and here I need to do one more. Need to make one more deviation from from this discussion. So this service export and service import capability is not something Submariner specific. So Submariner in this specific case serves as an implementation of Kubernetes enhancement proposal called multi-cluster services. So this is the proposal on which a special interest group works that allows you to describe in using common objects, those objects of type service export or service import. You can see, you can tell that it's still in works because it's an alpha API. So this is sort of generic objects developed by Kubernetes community, and Submariner just happens to implement the way those objects are supposed to work. So what this proposal tells us is that you can, if you have somehow connected to clusters, you can expose a service from one cluster to others using this service export object created in the same namespace with the same name as the service that you want to expose. Let's do that. Let's expose a service that we created in AWS cluster. We just create this service export object. So what happens now under the hood? So under the hood, Submariner will notice that this object appeared here in the AWS cluster. It made necessary route and DNS changes to make sure that inside of this cluster packets will be forwarded correctly. And then it shared this service export object in the broker namespace. Now, the other cluster or Submariner running in the other cluster notices this object, understands that this object, that this exported service needs to be made visible in the other cluster, in Azure cluster, and it creates corresponding service import object in that cluster. And according to that service import object, it sets up routes and makes sure that DNS can serve that object. And now this exported service can be available, can be seen under the common address. So again, it follows a standard convention: service name, namespace, SVC, and then as a domain for that service, we have something which is not intersecting with any of our clusters, namely cluster set.local instead of cluster 1 local and cluster 2 local. And we can check that it works. I think by that time it already established all the required changes in the configuration. So we can see that now connections to this DNS name work from every pod running in every cluster. Okay, so that covers basic Submariner capabilities. So what we didn't touch in a lot of details is well, mainly failover and load balancing and CNI support. Also Submariner support for different VPN technologies. With failover and load balancing, it would be interesting, for example, to see how Submariner can work when active gateway is down, for example, how it switches, or Submariner capabilities to use load balancers to connect to those gateways. So you can set up or use Kubernetes capabilities to set up a load balancer with a single endpoint that will still serve both gateways and will route packets from outside to the active one. Also, Submariner has support for multiple CNI plugins. In most cases, it works in a unified, uniform manner, just by Submariner setting up routing correctly. But for some CNI plugins, it can use their specific capabilities, like I think for OpenSwitch CNI, Submariner has some special treatment and can optimize networking using that CNI plugin capabilities. Another interesting thing about Submariner is that it can use different VPN technologies. So by default, it will use StrongSwan, I think, as a VPN, or IPsec. But it can also use WireGuard, or it can use VXNet packet encapsulation, which is not really a VPN, it's just an encapsulation. It doesn't encrypt packets, but may be a useful option in situations where you already have protected connection and you want to optimize for speed rather than security. Okay, and there are a few references that you may want to look through if you want to learn more. And here I think we're open for questions.
Thank you so much, Oleg. We have very good questions. I do have a question. So the IP addresses, do they have to be different for the two clusters, for the pods, or can we have the same at the pod CIDR? Yeah, right there.
Yeah, so they don't have to be, but if those address spaces intersect on any level here, you will be limited to exporting services manually. So you would have to create a service export object to make your service visible in other clusters. They won't be visible automatically.
Okay. All right. And the VPN technology, can you go over that one more time? So what is so can this be like any, like you said, open VPN or anything?
Yeah, I think it supports out of. I don't think it can support any so technologies other than what it's built with, and it supports out of the box IPsec, WireGuard, and non-encrypted VXNet. Or VXLAN, I'm sorry.
Okay. Any big like if somebody was to take up this kind of a task, let's say, what would be some of the gotchas or important things to keep in mind? Costs, like, or something else that you have in mind?
Yeah, that's a good question, because always that all looks great in principle. You sort of get your flat network space, but you always need to be conscious of inter-region, inter-site data costs, because usually cloud providers, even AWS, when you send data between regions, charges you extra. So it costs much more to send gigabyte of data between regions than sending the same gigabyte within or inside the region. So but it all depends on the use case. And of course, latencies and throughput are an issue. So it's easy to forget about that when you get this connectivity working in principle, but your network will still be segmented. So there will be a segment where you have very low latency and high throughput. There will be routes where throughput is limited. and the difference may be very drastic. So like from gigabits per second here to maybe megabits or dozens of megabits between regions.
All right, awesome.
And yeah, another important thing to remember is those failovers, failover, and etc. etc. So, like for example, if you lose an active gateway node, clearly connectivity is broken here, and it's broken until Submariner can coordinate a new active gateway node and reconnect, and which means usually seconds to minute. So if you have very critical applications where you cannot afford losing connections for more than a few seconds, hardware solutions need to be considered.
Okay. All right, awesome. Well, thank you so much. I think let's wrap it up. I don't see any further questions. So I'm going to go ahead and upload the. Oh yeah, there's a Jim Brent saying, "Well done." So thank you so much.
Thank you, Jim.
We're going to go ahead and upload the video recording and the slides on community.cncf.io/Washington-DC page. So look forward for that, and do join and ask us questions for future sessions. We already have one session planned for 2 weeks. We have another speaker coming up from Portainer in the next couple of weeks. So look out for that invite as well. Thank you, everybody, and have a nice day.
Thank you. Thanks for joining. Bye.